we can start. So I'm Vincenzo Alba. I will be the chairman for the second morning session. So we start with Benoit Vermersch, and he's gonna talk about probing quantum states in logical experiments with an upgraded randomized measurement toolbox.
Thank you very much. I'd like to thank the organizer for kind invitation. So I'm from Grenoble. I spent the last few years at the University Grenoble-Alpes, and 2 days ago I started a leave in Cobly, which is a startup in Grenoble. This startup is about building quantum computers based on spin qubits. There's a long tradition of quantum dots and condensed matter in Grenoble. And the idea is to try this big challenge of making a few qubits, making them interact, and hopefully run some algorithm on it. Then roadmap. What I will do in my case is, of course, more on the theory side. So we are building a quantum information team. The goal would be to continue what I was doing at the university, so developing measurement protocols to try to benchmark multi-qubit systems, so from 10 qubits to 20, hopefully to hundreds. At the same time, we have to develop simulation tools to make predictions and to compare with experiments. Most of that will be about tensor networks, and we will have quantum algorithm activity. Okay. But today I will talk about the university work. Okay. I will first introduce some ideas on how to measure entanglement and why we think it can be useful in different setups. Then I will present last results on measuring entanglement of many body states with polynomially many measurements. This is the core of this talk. And if I have time, I will show some experimental measurements on large-scale quantum computers. So I will first focus on pure state entanglement for simplicity. Then I will discuss mixed state entanglement. So for pure state entanglement, we have a closed system AB, and we are trying to see if A is entangled with B. And we know that this can be assessed by looking at the density matrix on the subsystem A, for example. And how to quantify entanglement of A versus B is done by calculating the entropies of this density matrix. Von Neumann entropy is the most famous one. And any entropies may be less famous, but they are easier to measure, and I will focus on these guys later on. So what does it tell us about entanglement? In quantum information theory, you can show that this is the right quantity to see how much resource you can exploit to, if you want, distillate Bell pairs and so on. Maybe more importantly for this workshop, in quantum simulation, you can quantify entanglement and distinguish different quantum phases based on scaling relations within entanglement entropy. You can have area law in the ground state, universal contribution to the area law in topological phases. You can see that entanglement will grow as a function of time in thermalizing systems, or grow logarithmically in MBA system, as we have seen before a break. What I also like about entropies is that they tell us about computational power of classical simulations. So one can show that if entanglement is finite in 1D, tensor network simulation can represent this state efficiently. Meaning, if you can do that, there is no use of a quantum computer in principle. So that's something about computational complexity, which is important. So now we focus on the second RENI. We know it's quantify entanglement. It's the log of trace row square. Trace row square is called the purity. And for mixed state entanglement, you can also show that the purity is a useful object to detect state entanglement. So based on these two items here, I'm interested in measuring the purity. And I want to emphasize that what I will tell you about the purity can be also applied to other quantities, like the kind of protocols that I will describe. I will illustrate them for purity, but you can also use them for more refined entanglement measures. So now I jump to an experimental measurement of the purity. I start by showing you the experimental recipe as it is done now on quantum computers. And then I will explain a little bit of technical details. But this is the experimental recipe. It's called randomized measurements. And it's instructive to divide what happens here in two steps. We have first data acquisition. So this is really the experimental work in the quantum experiment. You have first one step of calibration on a state which is well defined. Here it's all zeros. We will apply single qubit rotations, which are random unitaries, single qubit rotation, in the presence of noise. And if you want, these unitaries are there to measure the state. And you are trying to do this calibration to learn how well you can learn the state with such noisy unitary. This is why it's called calibration. And this calibration gives you calibration parameters that you can use then for the actual measurements on the state of interest. Okay. So now I'm performing an experiment on an unknown state. I want to measure entanglement. I will apply the very same unitaries. And based on that, one can show that this setup is information complete. So you can extract any physical properties even in the presence of noise in this measurement. This step is unity defined independently. Yes?
Are you assuming that the noise is state independent, so that the noise that you're assuming?
Yes, I make this important assumption. The assumption here is it's called gate independent noise. So the noise channel is dependent on the U. That's an important assumption, and then we have to verify it's true. It's exactly true for measurement errors and also for depolarization errors. And in our case, we can discuss that. Very good question. Yeah, so I was saying this step is unity defined. You will always do the same thing, okay? Independently of the quantity that you would like to measure. And then comes the next step, which now depends on the quantity that you would like to measure. It's the post-processing step that happens on a classical computer. While you analyze the data, you are using the knowledge of the applied unitaries. And you can also do some extra assumptions. I will describe this in the second part of this talk to estimate properties of the quantum states. This is how it's done. The nice way to analyze this data, now I focus on the post-processing, is called classical shadows. You may have heard about it. The idea is to take my measured states, these are bit string S, take the unitaries that I applied, take the calibration parameters that I measured in the first step, and build an object which is a classical shadow. It has a nice tensor product structure. And the key equalities is this one. Expectation value, the classical shadow is equal to the density matrix. It's an image of the quantum system, and you may want them to take many classical shadows to estimate functions of the density matrix. So you will never actually measure the density matrix, but you will use this statistical relation to build functions of the density matrix. And you can try to study statistical errors in doing this using random matrix theory. So I give a few experimental collaborations of this type of measurements, which was done recently. Here on the left, you have an example of this robust purity measurement, which I explained, where you have this calibration step and then you learn about the noise. This was a collaboration with IBM, where you can see that we measure purities of something which is not that far from 1. Here I'm looking at the purity of a total system, so my hope that it's 1. So that's the first message. The second message is you can achieve system size of order 12, 13. So we are beyond the reach of tomography by a lot. And we can try to say something about many-body physics. This was 1D. Another collaboration now with Google. You can now try to study entanglement scaling, as I was telling you, in quantum phases of matter. And in this example, the Google team was able to demonstrate the presence of an area law in 2D for the ground state of their hardcore boson system. And you can see here that you have Rayleigh entropy as a function of system size. Okay, this is small system size here, but you see a clear difference when the C state is at low temperature versus high temperatures. I think it was a nice, unambiguous demonstration of area law in 2D. And last example is something Manoj will also explain briefly. You can use this tool to study out of equilibrium physics. In this example, it was in trapped ions, a study of entanglement asymmetry. It's not quite the same as purity, but it's very related. And basically, when this function is 0, it means your system has thermalized. And what we have seen in this example is the so-called quantum MPMBA effect, where a state which is initially far from being thermalizes faster than a state which was initially closer to the steady state. Curiosity, and we can discuss about this later. But
sorry.
Yeah.
What does it mean, standard shadows there?
Standard shadows is I'm using only acquisition on an unknown state. And in this formula here, I assume there is no noise, so I put f equal 1, my calibration parameter.
And in this part, could use also multi-site unitaries, no?
Multi-site unitaries, yeah. It's possible, it's a different formula. And, it has been done in one experiment at the moment, yeah, IBM. So to conclude this introduction, we have a nice method. You saw that I can achieve n of the order of 12, maybe 15 in some cases. It's important to note that there is an exponential scaling in the number of measurements I need to achieve a certain accuracy. And typically it's scaled as 2 to the power n. So that's why I can do 12, but I cannot do 20. we have some robustness aspects which are interesting and understood, I would say. The purity has been measured, but many other quantities can be measured and have been measured for the first time using randomized measurements. And this is basically what I want to say about current randomized measurement techniques. Okay? Kind of expensive, but useful at the moment in some experiments. And now I move to the actual new result, which I would like to explain. How can we move from an exponential scaling to a polynomial scaling in number of measurements for measuring entanglement? And the result that I will prove is that there is a solution to a so-called quantum marginal problem, that I will explain. The idea is the following. I have a very big system, extensive system in 1D. I would like to try to find a formula which relates the purity of this very big system to the purities of the subsystem. If I can find this formula, I will propose to measure the purity of the global system based on measuring the purities of the subsystems, which I can measure principle. And after I measure these subsystem purities, I will be able to plug this into a formula to access the purity of the global system. Okay. That's the idea. And I will illustrate this formula with a very simple toy model using tensor network notations. So if you are familiar with that, it will be very easy. If not, I will try to do my best to explain that. So in tensor network models, you represent states and density matrices with graphics. So here I give you an example. 2-qubit density matrix. I can write this as follows in a basis. So I have two indices for the density matrix, Bra and Ket, as you know. I represent this with one box, two legs, okay, S and T. Then I can do a unitary evolution of the density matrix. Rho is transformed to U, rho, U dot, as you know. Mathematically, it means I have this kind of summation for the indices of the density matrix. It starts already looking ugly, right? So we like, in terms of network, to represent this graphically. I have rho, I have S and T, the initial indices of the density matrix. I contract this with U and U dag to obtain S prime and T prime. That's the root of this game so far. And then, of course, I can move to quantum circuit. And in this toy model, very simple toy model, I will consider 12 qubits. Initially, I assume they are in a mixed product state, so it's rho tensor rho tensor rho. I apply 2 qubit gates. Here, these are these 2 qubit gates in 2 layers. That's the simplest toy model I can imagine for a mixed density matrix. And in my example, I will be interested in the subsystem purity of the first 6 qubits. So what's the density matrix? The purity is now an object like that. So I have trace of rho A squared. Okay. So first, I take one rho A, and I will trace over B. So I will make the trace. It means I will contract this index here with this one, side by side. So that's what I indicate with this red color. I do the same for the second rho A. So it's rho A times rho A. And the matrix multiplication rho A times rho A is matching this row index with this column index, as you do in matrix multiplication. And then trace. Okay. So that's the tensor network diagram that we have. And then I will be able to simplify this to see if this purity of a many-body toy model has some structure that I can exploit. And what I will use is very simple, is that U times U DAG is equal to the identity. So this tensor network contraction is simple for us. And when you do the math, when you do the contraction, you end up with this very simple tensor network. The purity of a 6-qubit is a product of 6 numbers. Okay, so you see this, the tensor network is factorized. So I have one number times the second number and so on. And people from many-body physics in this audience are not surprised if I have an extensive state. I have extensive contribution to the entropy. These are these terms, right? And I can have one term which is the H term, which illustrates the connection with the B part. And for us, this was the insight. We have some structure in the purity of yes, thanks. Tensor network of a many-body quantum state, and the rest is kind of easy. We can try to use different subsystems and try to find this formula, which I promised. There is a formula for the purity of a global system as a function of the purity of a subsystem. And this formula is written here. You take an arbitrary n. You can divide it in blocks of size k. And the formula for purity is that you take on the numerator purities of 2 blocks, A1, A2, A2, A3, and so on. And you divide by purity of single blocks. And this is an equality for the toy model, which allows you to measure the purity. Now I have to show that it's not only true for the toy model, it's true for interesting many-body states. In this case, I will skip the derivation, but what we proved is that for so-called matrix product density operators, which are tensor network models which represent thermal states, this formula is also true up to exponentially small correction. So this was the second result. And the third result is that what I explained briefly before, that you can turn this equality into a measurement protocol, is also true. So you can measure subsystem purities efficiently, put this estimation in the formula. If you do the error propagation or statistical error inside these big formulas, you will see that statistical errors can be efficiently assessed.
But you still have the assumption that it's short-range entanglement, right?
Yes.
So if you don't have this one, you cannot say anything.
I start with the assumption
because for many systems, this is not short-range entanglement.
Yeah. So I will turn then to experimental procedure to try to see this convergence a bit later, if it's okay. So under this assumption, it's totally correct. We can measure the purity efficiently in a many-body system.
Sorry, just to understand the parameters. So you have a certain interval of size L.
L is the system size.
The whole system.
I changed my notation, so
Okay.
L is the total system. M is the number of measurements, and K is the block size, or divide.
The size of the interval doesn't play a role here.
It plays a role, a very important role. The number of measurements scales exponentially with the size of the interval. It's very important. Okay, so this I will skip. You can do this also on for mixed state entanglement, not the purity. I had 5 minutes of questions, or I'm done.
You are almost done.
Okay.
You are in the meeting.
Okay, I'm in it. Okay. So I just wanted to show that we did the experiment on IBM, and to give you an idea, we implement a 64 1D cluster state. And the goal was to try to measure the purity of this massive 64 qubit states. And this is a way to answer Antoine, how to try to see if the system has short-range correlations. Our proposal at the moment is to try to do this measurement for several correlation lengths. And at some point, you will see that the estimated purity will converge as you increase the K that you put in the formula. And in this case, a very simple state, we saw that it could actually converge, and we saw that the purity is exponentially small. It's 10 to minus 3. But it's also not that small, because if you take purity of a t equal infinite state, it would be 10 to minus 40, something like that. So in this experiment, we see small purities, but I would say these are still pretty clean many-body quantum states, and the goal in the future would be to try to use this entropy meter to understand better entropies in the large-scale scenarios. Thank you.
Can I ask what is the scaling? I mean, okay, you showed it in tensor network. Okay, that's completely believable. But what is the scaling with the depth? I mean, if we keep going with your coin model, right, you have to duplicate. What is the scaling between the depth and the size of the block, such that the error is suppressed?
You can show with this same model increasing the depth, but I think the K has to be twice the depth.
Twice the depth.
It's linear.
Because it's the light constant.
Exactly.
Can you go to the bound again?
Bound depth.
So, I mean, so K is like correlation length.
Yes.
So, by the way, this you could express this for a, in a sense, if you find a K, you have a tensor network. You have a, I mean, if you're 1D, your state is not multiple state, right?
Yeah, but two solution.
But so this K has 2 to the 4K, so it's worse than the 2 to the
So that's the an exact bound. It's very large.
Okay.
We know that in practice these bounds are not tight.
Because the idea is that you only need 2 to the n, right?
Yeah.
If K was equal n, actually, sorry, L. If K was L, I mean, if you have a
so the 2 to the n that I showed is based on numerical simulation, where we saw that analytically we can show 2 to the power 4 n. It's a difference between the exact bound and the numerical observation.
Which is a trivial result, right?
Yeah.
Because you just measure all operators in the system.
Yeah. So these bounds, in our opinion, is not tight. Also, we free there. We made some. There's a step in the derivation of the bound we are not very happy with. We actually free there.
If you have higher order than the entropies, the cone also spread more, right? So if you have Rennie 3, Rennie
Spreads more. I don't remember that. I could check this. For sure, this type of protocol we will use at low order anyway. So this part will explode very quickly with the order. About the cone, I'm not sure actually. Perhaps we can discuss.
Can I ask a question?
Yeah, there is no other question. So
Okay, but as a follow-up on my question, but then if your state is in multiple states, there are actually efficient way to actually measure them. Yes, no, I mean this like
pure state.
2010.
Yeah. So we are trying to do this for the mixed state scenario. That was the idea. For MPO, there is no
Okay.
actual proof.
So basically, you extended the result for FES for MPO. In a
Yes,
sense.
we are not extending the whole result, but some part of it, yes.
yeah, one last question.
Engagement.
It's,
Yeah. So it would be interesting to compare the cost of, tomography for MPOs that I think is efficient. I'm not that expert, maybe Jacob knows it better, compared to, the cost of computing the theory. Because in principle, you can learn whatever you have, then compute the power with a classical cost. So that would be interesting to compare these two costs, unless you already did.
Yeah, so that's ongoing work here with student Matteo. For NPO, there is no analytical proof at the moment, but the procedure is efficient.
For tomography, you mean?
For NPO tomography
Oh.
with local unitaries.
Oh.
So what we have done, we have extended our work to show that NPO tomography is also efficient. But it's ongoing work.
Okay, thank you.
You can check what it was.
Maybe one last question.
Is there, so there's about Renyi entropy, then there's also this other protocol with this interference, right? Is it also Renyi entropy? And I was wondering, is there some fundamental reason that it's like impossible to measure von Neumann entropies except for state tomography, or is that just that nobody has come up with a protocol yet?
So first, what I explained here with this formula can be applied for 2-copy experiments.
Yeah.
And the advantage is that you will be able to measure exponentially small purities. That's something which was not possible with a direct measurement with 2 copies. And then I know that there are many people working on estimating the von Neumann entropies from Renyi entropies. And it's not an easy task. Yeah.
Okay, let's thank Benoit again.